Yes, hi, I'm Agnes. You can also call me Aggie if you prefer the Hungarian nickname. So this is an idea talk and it's ongoing work, and we just wanted to sort of discuss some problems we've been thinking about in testing quantum programs. And we're trying to use some foundational results from quantum complexity theory to inspire the design of quantum programming languages. And this is joint work with Charles Yuan and Chris McNally, who are also here. And we're all students at MIT. Let's begin by discussing what I mean when I say verifying quantum programs, because I'm going to have a few different versions of verification in this talk, and it can get a bit confusing. So what I'm really going to mean is I have some quantum circuit, and at the lowest level, I have some intermediate state that I'm interested in. And this intermediate state is potentially some important state in my program that I would like to reason about. So I can define some predicate P that is related to a property about the state. And vaguely speaking, these properties might be something related to superposition or entanglement, or potentially I want to put some constraints on my amplitude and basis vectors. And so there's a few different ways that I could go about this currently. I could try some sort of benchmarking method, such as swap tests or sampling my states. I could do a version of mechanized circuit reasoning, so static verification. I could do state tomography and learn the entire state. Or I could do some sort of logic-based reasoning. And there's been some work where these foundational logics give rise to dynamic assertions. And so today in my talk, I'm going to be focusing on testing quantum programs as opposed to static verification, because currently our methods are a bit limited for testing, and it would be really nice if we had some quantum alternative to some of our classical testing and debugging methods, just to make development easier and more smooth for different people trying to program quantum computers. And our idea is that we need to insert sort of a new type of verification. And in this talk, I'm going to call this interactive verification. Okay, so let's take a look at an example that sort of motivates why we need a new form of testing quantum programs. So you may be familiar with the Haro-Hasidim-Lloyd algorithm for inverting linear systems of equations, and the details here don't really matter, but the point is that at the end of the algorithm, I'm going to get a quantum state that contains my solution vector to my linear system. And in this algorithm, I have this particular intermediate state, and I chose this intermediate state because it really sort of summarizes the desired functionality that an implementation of the HHL algorithm should include. So let's break down what this state might look like. I've denoted here in yellow the eigenvector register. So this register contains the eigenvectors of my matrix A that I'm trying to invert. W stores the eigenvalues, and these beta j's are the amplitudes of my vector B in my system of linear equations Ax equals B, decomposed in the eigenbasis of A. And this ancilla bit here is actually what does the inversion of the matrix, because matrix inversion is nothing else but applying the inverse function to the eigenvalues of some matrix A that you're trying to invert. And you can see here that in the denominator of the amplitude of the one state, we've inverted the eigenvalues. And then there's some additional steps in the algorithm that actually converts this into a form that gives you a solution vector, but those don't matter so much for us in this talk. So there's a few different properties that we might like to check about the state. And now I'm going to focus on the eigenvalue register. So I would like to ensure that my eigenvalue register actually stores the eigenvalues of a matrix A. And by that, I mean the eigenvalues corresponding to the eigenvectors that it is entangled with in this intermediate state. And why do we actually care about this? And how might there be a bug that would lead to some sort of error for which we actually need to do testing? So this intermediate state is prepared by the quantum phase estimation subroutine. This is just some pseudocode showing that, but The part that matters is the second bit, where you're applying a controlled rotation. And let's say we have a very simple bug, such as we put j minus 1 instead of j. It's a simple indexing error. But this would actually be detrimental to our correctness of our program because it would shift our eigenspectrum, and we would end up with some sort of nonsensical eigenvalue in the jth eigenvalue, and we would get our mappings from eigenvalues to eigenvectors to be incorrect. So it'd be really nice if there was a way to test this sort of bug. And again, there's a few things we could try. So state tomography, we learn what the state is through repeated measurements, but this is computationally very expensive, and also it requires an explicit definition of the eigenvalues. So we need to know actually what eigenvalues we're looking for, even if I have full information about the state. If I'm running some classically intractable instantiation of HHL, where I'm really trying to invert a matrix where I can no longer invert that easily, then the eigenvalues I would read out, I have no idea if this is correct or not, because I don't really know what I'm looking for. And so I could do something like projective assertions where I project onto the subspace spanned by the eigenvalues. But this is highly entangled and difficult to implement projection. So I could construct an approximate version of this that's outlined in this paper. But still, I have this problem with what am I actually trying to project onto? And for this, I need, again, an explicit definition of my eigenvalues. And if I'm running a classically intractable version of HHL, then I won't have these eigenvalues in my hand. It's sort of hidden, and it's unique to what only the quantum computer can understand and process. And we run into the same problem with even benchmarking. So let's say I have a correct execution of my program, and there I still need to define what my correct eigenvalues are. And even if I try to do a swap test there, I need to be swapping with some register where I know that those eigenvalues are truly those of the matrix A that I'm trying to invert. So there seems to be a fundamental problem here when we're thinking about programming quantum computers. And in this specific example, the issue is that these eigenvalues may be classically intractable. So if we're running some actually relevant instantiation of HHL, then at that point, my eigenvalues are sort of hidden from me as the developer. And this prevents the typical use of unit testing, where in this case, it's really a quantum input, classical output pairs that we can test. Because if we have some sort of intangible quantum state that's a quantum output, we need a way of classically testing quantum states. And this turns out to be a pretty difficult problem. So why is this a difficult problem? Well, these locally observable properties don't always align with what we would like to test for correctness. So in this case, we would like to be able to somehow hold the eigenvalue register, but I don't have a notion of what it is that I'm looking for. And so we need a way of collecting information about correctness during runtime without actually interrupting my runtime execution and reading out from the middle of the computation, because there might be hidden information at that point in the program that only really makes sense to me with reference to completion of the program. And there's really a bigger problem here. So my quantum computers live in a significantly more powerful computational model. And this information asymmetry leads to this classical quantum barrier. So there's a lot of fundamental challenges that arise from this in quantum algorithms to complexity theory to programming languages. So in algorithms, how would I input or take anything out from my quantum computer if the state space is exponentially larger and if it's in BQP and I'm just a BPP machine? In complexity theory and quantum programming language design, we're going to focus on these two categories today and see why the classical quantum barrier there is really difficult to deal with. And it turns out that interaction can help fight this barrier. And we're going to first take a look at how interaction has been very helpful in verification and complexity theory. And we're going to outline an idea we've had for adopting some of those techniques into testing quantum programs. But this idea, again, it's being worked out. So I'm very open to discussion afterwards and questions and everything. Okay, so we have this very nice result from complexity theory, which is that BQP equals QPIP0. What does this mean? Well, BQP is bounded quantum polynomial time, and QPIP0 is quantum prover interactive proofs with a classical verifier. The 0 just means that the verifier is purely classical. It has access to exactly 0 qubits. And Mahadev in 2018 showed a really beautiful protocol under cryptographic assumptions. This result holds. And the way in English language that you can interpret this is that all of the decision problems in BQP can be verified by a BPP machine with some sort of interactive proof. And if you're not familiar with interactive proofs for today, just think of it as some sort of communication back and forth between a classical verifier and a quantum prover. But we'll go through a bit in a second. So how does this, why would something like this actually work? Well, when you have a prover trying to prove something to a verifier, you need a witness to that program. And so I have my circuit that I'm trying to verify that some prover executed correctly. And I can represent the circuit using a Hamiltonian. And this was shown by Kitaev in 2002. And then Kitaev also showed that whether or not my instance X is in the language is exactly mapped to the energy of this minimum energy eigenvalue of my lowest energy eigenstate of my Hamiltonian representing my circuit. And so verification is reduced to finding the energy of this lowest energy eigenstate. And this is what the interaction actually does in the Mahadev protocol. So let's take a look at that. Oh, sorry. First, so this would be pretty easy to do, right? If I had a quantum verifier, because then the quantum prover could just send my quantum verifier the lowest energy eigenstate. The quantum verifier can make a measurement and read out, okay, do I have an eigenvalue that's sufficiently small? And then I can decide whether or not X is in the language. But things become significantly harder when I have a quantum prover and a classical verifier. And this is where the Mahadev protocol comes into play. So here I have this computational barrier, and interaction here helps us recover this lowest energy eigenstate. So the verifier is convinced by the prover that the prover somewhere in its Hilbert space, it contains this sufficiently low energy eigenstate. And through this interaction, the prover should convince the verifier of this. And the way this works in the Mahadev protocol is the verifier first asks the prover to make a cryptographic commitment to this quantum state. And then through a series of interactions, the verifier and the prover, at the end of these interactions, the verifier can sort of test what the prover was doing and see whether or not it actually, in its space, contains this lowest energy eigenstate. And the intuition here is that assuming that quantum computers can't break a crypto assumption, which is in this case learning with errors, which is basically just a noisy system of linear equations, the verifier is able to detect this cheating prover, and therefore it's able to estimate the lowest energy eigenvalue of the Hamiltonian. So how might this help us out in actually testing quantum programs? Because it seems like interaction is very helpful for sort of alleviating this information asymmetry that exists in the quantum complexity theoretic setting. And there, it's not just interaction that's helpful, though. It's also cryptography, and bounding the prover's abilities is actually executing the program that we're delegating. So we're going to talk about how, in our case, maybe we'll have to lift some of those cryptographic assumptions because they are difficult to implement. But let's just go through our idea for maybe how we could adapt some of the intuition gained from complexity theory. So again, we have some quantum circuit, and this represents our program. And we can write down a Hamiltonian that corresponds to that circuit using like a Kitaev circuit Hamiltonian reduction. But then we'd like to add this additional term into our Hamiltonian that represents our assertions and places constraints on the program execution between time steps I and I+1. And this joint Hamiltonian that represents both our program and specification, we'd like to somehow make it so that the lowest energy eigenstate of this is the witness to a correct execution of a program with respect to a specification. And so there's really two phases to this that we need to explore. And if we want to go down this direction, then these really need to be worked out. But there's one that is we actually want to execute the program. And this is what happens at runtime. We execute the program as part of this Hamiltonian that's been modified with our specification. But then we also have our testing where this is where we interactively try to recover this lowest energy eigenvalue of H and see whether or not it meets the threshold and see whether or not we actually had a correct execution of our program during runtime. And so this would give us some sort of classical bit of information, like whether or not we're totally bug-free or not. And we're still trying to figure out how we may be able to actually encode into our Hamiltonian an assertion that tests states that is a greater set of states than what you can already do with existing methods. But I hope you've learned a little bit about how we may be able to use some of these foundational results from complexity theory and how this information barrier that exists between classical and quantum computation should be taken into account when trying to design quantum programming languages, because it leads to many, many challenges, as you've seen here. And we think that this will be part of the future of building quantum programming languages. So thank you.
Great. So we have a question over here.
The specification where you can encode assertions, can you sort of expand on what that would look like in the HHL example? And would you run into the same issue where you need to know the answer, namely the eigenvalues, to write that down?
Yeah, we're trying to figure it out. We think that there's some way to play around with specifying the subspace without actually directly knowing it, maybe relative to an orthogonal subspace. But that is where we're stuck, and we don't know if it's really possible, but we're thinking it is, and we're hoping it is. Like, the idea is that we're keeping our specification quantum and as part of the execution of the program, and we're not trying to read out classical information during execution. And we're hoping that in that way, if we make the specification an operator that's executed along with the actual algorithm that we're trying to execute, that will allow us to reason about a more diverse set of states than if we were trying to really just let's peek into the program and see what's going on.
Very exciting work. Thanks for sharing.
Yeah.
Thank you. Can you go back to the slide that said under learning with error assumptions, things can be done using VPP?
This one?
Can you,
oh. This one.
Yeah, can you say a bit more about this? I mean, I know this is your kind of assumption, but I'm trying to understand. So learning with error is not known to be hard, but it's believed to be hard. That's the first thing, right?
So it's believed that quantum computers can't break learning with errors. And that's a pretty reasonable assumption. And it's related to also lattice-based crypto, how you can't find the shortest vector. And
but it's not known, learning with errors is not known to be a computer thing like this, right?
No, it's not
okay.
proven, but.
That second part, all decision problems can be verified BPP. So basically, you can solve quantum problems using interactive proofs and a classical machine.
So you can verify quantum proofs. So given some witness to your computation, which in this case is the lowest energy eigenstate.
But can't you use that as an algorithm once you can? No.
Well, I guess that is sort of what we're trying to do, and like it's a protocol, right? So my personal belief is that there is a sort of future also in quantum algorithm design that it's not interaction in the sense the way that variational quantum algorithms are interactive. It's really it's sort of teamwork between a classical computer and a quantum computer, but not so much as let me just optimize and then like resend the same thing. But it's really back and forth communication. I do think there's a future in that, but who knows?
Very interesting. Thank you.
Yeah.
Last question for Robert. I just realized in the course of your answering that question that I'm a little bit confused because in general, using interactive proofs, we have an IP complexity class, and that's much bigger than BPP or BQP or
Right.
even NP, right?
Yeah.
So we are restricting the.
Yes.
How are we? So clearly, this is not just saying that, because then it would be trivial and
Right.
there would be no assumption. So what's
Yes.
the restriction?
So BQP is contained in IP. So
Yes.
yeah, but in that case, you have an unbounded prover. And here we're bounding our prover to BQP because in a quantum computation, our prover is BQP. And this results, so really what we would like to prove is the relation between BQP and IP BQP, where soundness is against an unbounded prover. But we don't really have that result yet. So here what we've said is this is both complete and sound against BQP machines instead of unbounded.
So there's actually quite a small complexity class. It's only it's sort of below BQP and above BPP, because the prover is simply a BQP prover. Is that right?
Or what do you mean by small?
This complexity class only contains a small number of things that are not in BPP, presumably, compared to something like IP.
Oh, yes, I guess so. Yeah.
You can keep the conversation going, but you're talking.
Good point.
Oh,
Well, thanks very much, Agnes.
yeah.